All right, let's jump straight into this explainer and demystify the real hidden bottleneck of AI model training. You know, when we think about ultra-scale AI, our minds immediately go to massive clusters of GPUs crunching numbers at warp speed. But honestly, what we almost always miss is the storage and data input pipeline, the actual supply chain that's feeding those compute engines in the first place.
So we've got to start with a really painful and, frankly, super expensive question. Are your high-end GPUs literally starving for data? I mean, imagine building a lightning-fast factory assembly line, dropping millions on the absolute best equipment, only to leave those machines sitting completely idle because they're just waiting for raw materials to show up at the loading dock. Well, that is exactly what happens when your data pipeline just can't keep up with your compute power.
To put the sheer scale of this problem into perspective, let's just look at the hardware for a second. An NVIDIA Grace Blackwell GB200 rack, packing 72 GPUs, needs a massive 14 to 20 gigabytes per second of aggregate storage throughput just to keep those GPUs saturated. That is a staggering amount of data flowing every single second. And if your storage setup isn't scaling to meet that, your ultra-fast, incredibly expensive GPUs are just sitting there, twiddling their thumbs.
So, to fix this supply chain, here is our roadmap. 1. The starving GPU problem. 2. Bypassing CPUs with GDS. 3. DeepSeek's custom 3FS solution. 4. Tuning the data pipeline. And 5. Continuous profiling and tuning.
Section 1. The starving GPU problem. The broken factory. GPUs are absolute beasts, right? But they have a very specific diet. They absolutely love large, contiguous chunks of data. If you're storing millions of individual image files on your disk, you're essentially forcing the system to generate tiny, random reads. And those random seeks, they will quickly bottleneck your entire training run because the storage overhead is just way too high. Instead, you really want to group your data into large binary files. Think Parquet, TF record, or web dataset formats so you can enable fast sequential access.
Section 2. Bypassing CPUs with GDS, the delivery route.
Now, this is where things get really cool, because we can actually completely eliminate the slow middleman that's unloading the trucks. In a traditional setup, without GPUDirect Storage, or GDS, data coming from your NVMe drive hits a bounce buffer in the CPU's host memory before it finally gets copied over to the GPU. It's a detour. But with GDS, we establish direct memory access. The data flows straight from your storage or network directly into the GPU's high-bandwidth memory, completely bypassing that CPU copy phase.
And looking at the architecture here perfectly illustrates this bypass. Notice how the GDS path completely skips the CPU bounce buffer. Contrast that with the traditional path, where the data has to take this tedious detour through the system memory. By cutting out that middleman, you literally free up the CPU to handle other pre-processing tasks while massively speeding up data delivery. It's a win-win.
If you need hard proof of why this matters, check out these GDSIO benchmark numbers. By simply switching to the GDS path, throughput jumped from 8.0 gigabytes per second to 9.6 gigabytes per second. That's a 20% boost, just like that. And at the exact same time, average latency drops by 20%, going from 1.25 milliseconds down to a flat 1.00 millisecond. Basically, you get more data, arriving faster with less CPU overhead. Section 3. DeepSeek's custom 3FS solution. Massive scale. The engineers over at DeepSeek noticed a really critical issue. AI training workloads perform a massive, and I mean massive, number of random reads. Because of this, conventional data caching at the OS level isn't just ineffective, it actually gets in the way. So they decided to build the Fireflyer file system, or 3FS, completely from the ground up. By eliminating conventional caching, 3FS sends requests directly to the NVMe SSDs, bypassing the OS page cache entirely. Taking a look at the architecture of 3FS, we can see exactly how they pull this off. The meta and storage services are interconnected over an RDMA-capable fabric, stuff like InfiniteBand or ROS. This means the data paths completely bypass the kernel page cache and entirely avoid host-side memory copies. It delivers optimal throughput straight to the nodes that actually need it. And the bottom line impact of this custom engineering is just staggering. DeepSeek reported multi-terabyte per second aggregate read throughput hitting up to 7.3 terabytes per second in their environment.
In another benchmark, they managed to achieve 6.6 terabytes per second while simultaneously handling background workloads. Honestly, that is the exact kind of scale required to keep thousands of GPUs from starving.
Section 4. Tuning the data pipeline. The loading dock. All right, let's talk software. Here's your checklist for quick PyTorch data pipeline wins. Start by setting pin_memory equals true. This locks your data in RAM for high-speed, direct memory access transfers without hitting any page faults. Next, scale up your num workers to fetch data in parallel. Never let a single thread hold up your entire cluster. You also want to enable persistent workers equals true, so you aren't wasting precious time spinning processes up and down every single epoch. And crucially, make sure to tune your prefetch factor so your workers are always queuing up the next batches while the GPU is busy computing the current one.
Section 5. Continuous profiling and tuning. Quality control.
Performance engineering is definitely not a one-and-done task. It's a continuous loop. You always start by establishing a baseline on a single node. Then you profile the multi-GPU run using tools like NVIDIA's Nsight systems to find exactly where those stalls are hiding. Once you spot the bottleneck, you apply your targeted fixes, and then, this is the most important part, you ruthlessly remeasure to ensure it actually worked, without breaking something else in the process.
Now, if you're scratching your head wondering exactly where the delay is happening in your pipeline, try these isolation tricks. Temporarily set your data loader num workers to 0. This strips away all the background threading and shows you the pure, isolated cost of your Python data loading and transformation logic. Or, if you suspect the transfer itself is the problem, go inspect the copy lanes in Nsight systems. That'll measure the exact host-to-device transfer overhead, telling you exactly what needs fixing.
I really want this quote to just sink in for a second. You can spend weeks, even months, tweaking an algorithm or adjusting hyperparameters for a tiny, single-digit percentage gain in efficiency. But if your data input pipeline is broken, you could literally be throwing away 50% of your total compute power. 50%! Your GPUs are just sitting there completely idle, waiting for the trucks to arrive.
So, armed with a solid grasp of GPUDirect Storage, DeepSeek's massive custom file system approach, PyTorch tuning strategies, and a solid continuous profiling workflow, I want to leave you with this final thought. Where is the hidden bottleneck in your AI factory, and what are you going to optimize first? Thanks for hanging out with me for this explainer, and I'll catch you in the next one.